we are going to start a new topic of the second chapter, that is electrostatic potential energy. So as you all know that in the previous chapter we have discussed the electrostatic force between the two charges, right? And also we have discussed the electric field. So in this chapter, electric potential and capacitance, we are going to discuss the first topic, that is electrostatic potential energy. So potential energy concept you have got in class 11 also, that it is some kind of work done against a force, right? Say for example, if I consider an object, say there is an object on the ground, right? So this position is denoted by A. Now we want to take the object at the position B, so at a height h. So what we have to do, we have to do certain amount of work, right? And here you can see that the force due to gravity is acting in the downward direction, so that is denoted by m into g. So we have to do some amount of work against the force due to gravity. So this work will be stored in the object as its potential energy. So how much was the expression for that work done? So that is given by mgh, and this is nothing but the potential energy of the object. So what is potential energy? It is the amount of work that we have done against the force due to gravity to take the object from the position A to the position B. So this work will be stored in the object as its potential energy. So here this potential energy is known as the gravitational potential energy. Now the similar analogy we can draw for electrostatics also. Say for example, we are considering two charges. Let us take this is one charge plus and there is another charge plus, right? Now what will happen? Now there will be a force of repulsion, right? So there will be a force of repulsion between the two charges. But say suppose we want to bring the charge closer to one another, then what you have to do, we have to do certain amount of work against the force of repulsion. So this work will be stored inside the system as its potential energy. It is very similar to the previous example of the object which is taken at a height. So here also you can see that when two charges of similar nature are placed, then there will be a force of repulsion. So we have to do some amount of work against the force of repulsion to bring the two objects closer to one another. So this work will be stored inside the system as its electrostatic potential energy. So basically what is potential energy? The potential energy is nothing but the energy which is required to form any system, or we can say the amount of energy that is required to break from a system. So this energy is known as the potential energy. So when it is for the charge, we say it is electrostatic potential energy. When it is due to the mass, then we say it is the gravitational potential energy. The meaning is same. So let us try to derive the expression for potential energy now. Electrostatic potential energy. So for that we take a source charge capital Q, right? And you know that the direction of the electric field will be outward. So these are the direction of the electric field, right? From the positive charge, and we take a distance, say the distance we take like this, right? And here we place a very small charge Q, right? Say a very small charge Q is placed. Say the distance from the capital Q to the small q we have taken x, right? So this q we have placed at which point? Say the position here we have placed is infinity. So at infinity we have placed the charge small q. Now what will happen? There will be a force of repulsion, right? So there will be a force of repulsion between the two charges, so that is the force of repulsion. Now if we want to bring the charge small q closer to capital Q, then what you have to do? We have to do certain work against the force of repulsion. That means we have to apply a force, an external force against the direction of the force of repulsion, right? So this will be our external force. So this external force we have to apply against the force of repulsion. So let us take a very small displacement dx, right? And we want to bring the charge small q at a distance small r. This is our final distance. At this distance r, we want to bring the small charge q. So we have taken a very small displacement dx, and you can see that the direction of the external force and the dx are in the same direction. So what is the work done then? What will be the expression for the work done? Since the displacement is very small, so the work done will also be very small. So that will be denoted by dw is equal to f external multiplied by dx, right? So this will be the work done. So this I will write in a new page. So the work done is given by how much? F external multiplied by dx. Both are vector quantities, right? And here you can see that F external is equal in magnitude to that of the electrostatic force of repulsion. But when it comes the direction, then the direction wise both of them are opposite. So we can say direction of both the forces are opposite in direction, but magnitude wise both of them are equal. So now if we want to find out the total work done, then how to find out the total work done? So therefore total work done is given by, so how to find out the total work done? So total work done is given by simply integration, right? So what we have to do now? Integration. So here f external dx, and this will be cos of 0 because both the direction are same. So left hand side will be getting w, and right hand side it will be getting k. This is capital Q small q divided by x square into dx, right? So because the original distance was how much? X we have considered earlier. So it is x square multiplied by dx. So the limit of integration will be from infinity to a final distance how much? R. So we want to bring the charge q small q from infinity to a final distance r. So the limits of integration will be from infinity to r. Now let us solve this equation. So right hand side, if we do the integration, then k q will be constant, right? And within the integration sign, this will be dx upon x squared. This is from infinity to r. So on further integrating, we'll be getting k q. This will be 1 by x, right? Infinity to r. This integration, you can try this by yourself also. So after further calculation, you'll be getting how much? So this will be k q. This will be 1 by r minus 1 by infinity. And you all know that 1 by infinity is 0. So therefore work done will be how much? So that will be minus k q divided by r, right? So this will be the equation. So we have got how much? So work done we have got minus k q divided by r. Now there is a relation between work done and the potential energy. This relation you have got from class 11. So what was the relation? That work done by the conservative force is given by negative of potential change in potential energy. This relation you have got in the chapter work power energy in class 11. There was a derivation also, that work done by any type of conservative force. So here conservative force will be the electrostatic force. So that is given by negative of change in the potential energy. This is a very important relation. So we can write minus change means final minus initial, right? So if we write this one, then it will be minus uf plus ui equal to minus k q divided by r. Now we have to consider a reference point here. So we can write like this: ui is the potential energy at infinity. So why it is infinity? Because it is the initial potential energy and initial position of the charge small q was at infinity, right? So at infinity we are going to consider 0, and uf, let us take it u. So if we apply this two condition in the above expression, then how much will be getting? So therefore minus u plus 0 is equal to minus k q divided by r. So from here u will come out how much? So that will be k q divided by r. So this is your final expression of potential energy. So this is a very important derivation. Electrostatic potential energy is given by this relation, k q divided by r. So here you can see that the electrostatic potential energy is inversely proportional to the distance between the two charges. So that means it is very simple that if there are two charges, let us take this is q1, this one is q2, and this has been separated by a distance r, then the potential energy will be given like this, that it is k q1 q2 divided by r. This will be the electrostatic potential energy. So for any system of two charges separated by some distance, the electrostatic potential energy is given by k q1 q2 divided by r. So I think it is clear to all of you. Let us move to the next topic here. The next topic is electrostatic potential energy due to system of charges. So now we are going to find out a relation of potential energy that can be applied to a system of charges. System of charges means there will be a collection of charges, and we are able to find out the electrostatic potential energy. So collection of charges means we can take, for example, this is a coordinate system, right? This is a x, y, and let us take one charge is q1, another charge here we have taken q2, another charge here we have taken q3. The distances are r1, this is r2, this one is r3, so like this. So there are suppose n number of charges, and the distances from the origin is given by r1, r2, r3, like this. So how to calculate the net electrostatic potential energy? So this we are going to find. So there is a relation that is given for multiple charges. The relation is like this: the net electrostatic potential energy is given by, we can write like this. So that will be given by k, this is q1 first to charge, k q1 q2 divided by r1 2, right? Plus it will be given by second charge and the third charge divided by r2 3. Then it will be given by the charge 3 and charge 4 divided by r3 4. So it will go on like this. Okay? So this is the addition of all the potential energies between the charges. So if we write a single term, then the single term will be written like this in terms of summation symbol. So in terms of summation symbol, if we are going to write, then if there will be double summation because of two charges. So this will be k q I, this is q j, right, divided by r I j. So this will be the expression for net potential energy for a system of charges. This is a very important relation. We have to apply this in the solving numericals. So the net potential energy is given by this relation. Here there is one more important thing: I is not equal to J. Say if I is equal to 1, then J has to be equal to 2. If I is equal to 2, then J has to be equal to 3. So like this it will go on. So this is the net electrostatic potential energy for a system of charges. So let us try to solve one or two numericals based on this concept. The first question is, there is a triangle given and there are three charges present at the vertices. This is an equilateral triangle. Say this one is denoted by 1, this one is denoted by 2, and this one is denoted by 3. So what is the net electrostatic potential energy of the system? This is the question given, right? So what is the question? You have to find the net electrostatic potential energy. So how to find out now? So now here you can see one thing, that when we brought the charge q at the position 1, then there was no other charges. That means the work done to bring the charge q at the point 1 will be 0, because there was no other charges present at that time. And now when we bring the charge at the point 2, then there was already one charge present at the position 1, so we have to do some amount of work done against the force of repulsion. Again, when we brought the charge q at the position 3, then there was already charge at the position 1 and 2, so we have to again do some amount of work done against the force of repulsion. So the net work done is given by wq1 plus, we can say, wq2 plus, we can say, wq3. So when we bring the charge q at the position 1, there was no other charges, then work done will be how much? 0. Now when we bring the charge q at the position 2, then there was already one charge present at the point 1, so therefore the work done will be given by k. So that is q1 q2 divided by distance is how much? A, right? So there will be a negative sign, because work done we are writing, so work done, it has to be negative, right? Again, when we write the potential energy, then this will be positive. Then for the third charge, when we bring the charge at the point 3, then there was already charges 1 and 2 present. That means the work done will be k q2 q3 divided by A minus k q1 q3 divided by A, right? So this is the work done. So from here we can say that the net work done is how much then? So that is minus 3 times k q1 q2 divided by, sorry, all the charges are equal, right? So all the charges are equal in the question it is given, so there the charges will be equal. So if it is equal, that means we can say this is 3, that means we can say this is 3k q square divided by A. Now when we write the potential energy, that means it will be minus of work done, so that means it will become 3k q square divided by A. So this is the answer. So the net electrostatic potential energy will be how much? 3k q square divided by A. So this is the net potential energy of the whole system. So let us try one more question of this type. This is question number 2. There is a square given, right? And charges are placed. This is q, this one is q, this is q, and this is also q. The distances are equal only. A at A, let us denote it by 1, this is 2, this one is say 3, and this one is 4. Clear? So 1 2 3 and 4. So there are 4 charges which are placed at the vertices of a square of side A. So here also the question is same, to find out the net electrostatic potential energy. So here you see the diagonal distance. The diagonal distance will be how much? A root 2. And similarly this diagonal, the distance will be also be how much? A root 2. So when we bring the charge at the point 1, then there was no other charges. That means work done will be 0. So like this we have to do the question. So let us try the solution part. So what we can write, net work done will be how much? W q1 WQ2, there are four charges, right? WQ3 and WQ4. So when we bring the charge at the point 1, then there was no other charges, that means work done will be 0. Now when we brought the charge Q at the point 2, right, then there was already one charge, that means the work done will be minus K Q1 Q2 by A. Now when we bring the charge at the point 3, then there was two charges, 1 and 2, that means the work done will be K Q2 Q3 divided by A minus K Q1 Q3 divided by A times root 2. Why? Because now this time Q1 is the diagonal charge, so the distance will be how much? A times root 2. Again, when we bring the charge Q at the position 4, then there was already charges 1, 2 and 3. That means the work done will be like this: K Q3 Q4 divided by A minus how much? K Q1 Q4 divided by A and minus K Q2 Q4 divided by A root 2, right? So here root 2 will be coming because this time Q2 is the diagonal charge. So how much we'll be getting now? If we do the further calculation, that means there will be minus 4 times, right? So kq square divided by A minus 2 kq square divided by A root 2. So the net potential energy is negative of work done, so that means it will be plus 4kq square by A plus 2kq square by A root 2. So this will be the net potential energy. So I think it is clear to all of you. So when we get this type of questions, always follow this method of solving. So the net electrostatic potential energy is given by negative of work done. So first you calculate the total work done, then just do the negative. So this will give you the net electrostatic potential energy. So I think it is clear to all of you. Let us move to the next topic. So the next topic is our electric potential. So next topic is our electric potential. So what is electric potential? This is the definition is given like this, that it is the amount of work done, the amount of work done per unit charge, per unit charge to bring it from infinity to a point. So what is the electric potential? It is the amount of work done to per unit charge to bring it from infinity to a point. So let us try to understand this definition. So that means if there is one charge, say for example Q, right? So there will be electric field. So the direction of the electric field will be like this, right? Now say suppose there is another charge present. Say at this point P there is one charge present Q naught, and we want to bring the charge Q naught from infinity to a final distance R, right? So we have to do certain amount of work. So what is that work? So here you can see the electrostatic force will be like this, that is the force of repulsion, right? And when we want to bring the charge Q naught closer to capital Q, that means we have to apply the force in the opposite direction. So this will be the external force, just now we have discussed it. So for Q naught charge, if we have to do a work dW, then for 1 coulomb of charge, how much work we have to do? So it is very simple. So it is dW divided by Q naught. So this quantity work done per unit charge is defined as the electric potential. So that means dW by charge Q naught is known as the electric potential. This is the definition. So this is the definition of electric potential. You can see the SI unit also. So SI unit is given by joule per coulomb, right? So that is the SI unit of electric potential, and it is known as the volt. This is also known as the volt, right? So this is the